I will introduce you. You can be there or wherever you'd like to be. Good morning. I am thrilled to see so many people here on a rainy morning. We thought that most of you might turn into your streaming, so welcome. I welcome you, and I welcome those who are listening to us on a live streaming device. For those of you who may not know me, my name is Claudia Berry, and I am this year's president of HASP. The first thing in order of business in our housekeeping is that we all pull out our cell phones and make sure they're turned off, because I think our speaker today has so many interesting things to share with us, we certainly would not want to interrupt him. So check your cell phones, make sure they're turned off. Before we begin, and I introduce Dr. Boerigter, I would like to just go through a few announcements with you. First and foremost, our registration renewals have closed, and we have now 726 members. Our membership is not closed, but our registration, so thank you all. Thank you for those who got that done in time. Thank you to the people who volunteer in the office, who called some of us that may just need a gentle reminder to remember it's membership renewal time. And with that, I would just like to read the names of our newest members, and Josh, who's in the booth, has them on the screen behind me. My apologies if I mispronounce your name. I don't intend to, and I know that's very important. But I have to share with you, I am not Dutch, but I have been here a long time and I should learn correct pronunciations. The first is Linda Beacons, Chris Campbell, Brian Carter, Marion Neal Carter, Karen Dunn, Kathy Esposito, Laura Finsky, Chris Groth, Vern Hoeksema, Nancy Honor, Diane Coop, John and Kathleen Kersage, Carolyn Lambert, Karen Palmatier, Chuck and Patsy Postma, Deborah Self, Chuck Sickle, I think, Char Tinclay, Case and Elaine Vanderleest, and Kay Volverd. So we welcome our new members, and I want to share with you, let's give them a round of applause. And we are going to have a new member orientation on August 27th at 1 p.m. in the HASP classroom. Come and learn about all the exciting things that your membership with HASP are open to you, between classrooms, special events, trips, HASP Beyond the Classroom, and of course, our monthly program. So if you are a new member who has never been to an orientation, or if you are a member who has recently reinstated your membership, please call the HASP office and sign up to come to the new member orientation. Now, I don't know if you see, I don't think Josh has the trains behind me now, but if he puts the trains up there, you'll see, for all you train aficionados, that we have a trip to the trains of Chicago. And this is an overnight trip that includes tours at our newest national park, the Pullman National Park and the Illinois Railroad Museum. Lots of activities are planned, but I need for you to stay tuned tomorrow, because Amy's going to put an announcement out. we've had to change the date of this, not the date for registration, but the date that this special event trip is going to take place. So Wednesday, August 7th at 12 p.m., our registration will open, but we'll have a different date than what you've seen. Finally, there's been lots of questions about that wonderful fall catalog, and that is going to be put in the mail on August 20th, and fall registration will open on August 28th. Lots of great classes planned for the fall. Now, this is a note from Amy to all of you who may have recently moved. She writes to me, hint, hint, to the farmstead. Please make sure to call the office and update your mailing address. And now, on to our program for today. Today's program, Nuclear Fusion Energy, the Climate Change Solution. Can nuclear fusion energy be a solution to the threat of climate change? Could there be a better alternative to nuclear power? Every method that is currently used to generate electricity has a downside. Here are a few examples. Coal ash is toxic and radioactive. Gas can burn explosively and always contributes to global warming. Windmills fall in tornadoes, kill birds. Their reflections produce seizures for some people, and their blades do not recycle well. Solar panels have limited lifetime, include toxic substance, and are inefficient. Dams are not very effective during a drought. Today, Dr. Stephen Boerigter will review the basics for understanding energy coming from nuclear fusion for us non-physicists, and maybe we have some physicists in the audience, and will present an overview of the possible role of the energy source for our future. Dr. Boerigter recently retired from Los Alamos National Laboratory, where he served in a variety of both technical and non-technical roles for more than 29 years. He earned a Bachelor of Science degree in Geology Engineering at the University of Arizona and a Doctor of Science degree in Nuclear Engineering at Massachusetts Institute of Technology. He is a member of the Hope College Board of Trustees and currently serves as chairman of the board. He and his wife, Kathy, by the way, is a 1983 Hope graduate, have 3 grown daughters, 2 of whom attended Hope College. Some of you may remember Stephen and his wife from their 2022 3-month, 5,000-mile tandem bike journey they undertook to raise funds for Los Alamos nonprofits. His parents, George and Sabella, HASP members, were honored in 2016 with the establishment in their name of the Hope's Boerigter Center. It is my honor to introduce to all of you today Dr. Stephen Boerigter.
Thank you, Claudia. There, you had to say thank you to make sure that the microphone was working. So I can hear myself.
We're good.
We're all good.
Okay.
And thank you for that intro. We'll see how accurate some of that is when we get through this presentation and find ourselves in the place of a few conclusions. But today, for the next about an hour or so, we'll talk a little bit about nuclear fusion energy, climate change, I'm hopeful that today's conversation will be technically interesting. It shouldn't be, I hope, technically overwhelming, so that's the fine line we're trying to draw. So without any further ado, let's go ahead and get into this. Let's see if I can make all the technology work. There we go. We're going to spend a few moments just getting ourselves back up to speed about energy, because it's kind of important in our world today. And I'm going to talk about energy in the context of chemistry and physics. Now, it isn't really sort of precisely bound up into those two pieces, but it's easy to think about it that way, and we'll find it helpful. So I've shown a few graphics up here of various different ways we can think about energy in our world. And it turns out that all the energy in our world really comes from chemistry. You'll see in a moment a little more detail of what I mean by that. But we've shown a few things, and there's lots of energy in our world today. There's all the food production, there's grass and vegetation, which of course takes energy from the sun. And then we have transportation fuels, and we move around. We have the lights in the room. It takes energy to build this building, energy for us to be here. But all that energy, that all comes from chemistry. And so here's a simple graphic, and it kind of looks like the atom. It's the way we tend to think about the atom. You may remember, at least those of you who are somewhere between science and history, Lavoisier, back in the 1700s, came up with the concept of elements and molecules. He didn't use those exact words at the time, but we now know that our world is comprised of atoms. Those atoms have a neutron and a proton and a nucleus, and then they have electrons surrounding them. The electron is negatively charged, the proton is positively charged, the neutron has no charge. And I just should mention for a moment that this is a kind of a standard atom graphic, but it turns out that this graphic isn't really representative of scale, and that can be kind of important. It's been said, so if we take all the space out of the electrons and we just leave the proton and the neutrons, we can get all the proton and the neutrons together. That is, in fact, what a neutron star is. And it's been said that if we took a teaspoonful of neutron star, it would weigh as much as a battleship. We have to stop and try and wrap our heads around that for a minute, and it's kind of tough. In any case, that's the atom. And when we talk about chemistry and the energy in the world around us, here's what we mean in the context of the atom. We have the electrons. Let's see if I can make the little button point up there. There's some electrons revolving around the nucleus, and those electrons come and go, and they lose and gain energy as the atom binds to other atoms and we get molecules. And all of that movement is chemistry. That's the energy in the world around us, and all of that energy is what we tap into daily. That energy can have a tremendous scale. At the very smallest of things, very small biological molecules with millions and millions of carbon atoms and hydrogen atoms and some oxygen atoms, and yet we can have very tiny amounts of forces involved in that scale of that energy movement. The smallest ant, plant growth are two little examples, but of course on the other end of the scale, we can put other kinds of molecules together. Behind me is a photo of the space shuttle. That's 10 million pounds of thrust. Another way of thinking about that in scale is 10 million horsepower. If you thought about it as a car, it's a similar kind of scale. But that's still chemistry. That's still, in the case of the space shuttle's solid rocket booster engines, that's aluminum and some nitrates coming together and producing this extremely powerful force, all high explosives, of which it would take just a few grams of high explosive on the table in front of us to blow this room to smithereens. And yet that's all chemistry. Big scale. I'm going to go back to the atom for just a moment, and we'll talk about the nucleus. And so The forces that create that scale force in chemistry with the electron, that's called the electromagnetic force. The negative charge of the electron is attracted to the positive charge of the proton. But how is it, if the electromagnetic force is in play, how is it that the nucleus is held together? The nucleus has neutrons and protons, and they're very tightly bound. And it turns out there's another force in our universe. Pause for a moment. There are 4 forces in our universe. We'll talk about 2 of them mostly. The electromagnetic force, that which drives chemistry. The strong nuclear force, that's what we're going to talk about here, and I'll mention the others. And so the strong nuclear force holds that nucleus together, holds those protons very tightly together, neutrons, but it interacts only at very, very, very small scales, hence the size of the nucleus. But it is very, very powerful. And it is that strong nuclear force that we tap when we do nuclear things, fission or fusion. And for just a little bit of scale, well, let's see, I jumped ahead. Before we get to scale, let's talk a little bit about the nucleus here and what that force can look like. So, again, hopefully technically interesting, not overwhelming. On the graph behind me is something called the binding energy of the nucleus with the different number of protons and neutrons. And at the very lowest level is the hydrogen atom with some helium, another hydrogen that's with tritium, so that's hydrogen, see where you see the 3 in the H? That's 2 neutrons and 1 proton. It rises up quite a bit, stops at about iron 56, and then the graph starts to turn over. Interestingly, one of the implications of this curve is that if we wait long enough, I don't know, 10 trillion years, the entire universe will be composed of iron 56, and there won't really be anything interesting happening anymore. The other observation from this curve, while we'll mention it, is that the energy of the universe is really driven by stars, which is mostly in the form of hydrogen in the H or the H2, and it coming together. And it is that energy from the star, which then, because they're so large, has access to gravitational energy that comes together and then produces a supernova. And it is in that supernova event that we get all the heavier stuff. So any of the gold in our universe today, any of the other things heavier than iron 56 in our universe today, was actually formed in a supernova at some other place in the universe previously in time. And so, if we're going to try and tap that energy, that is from the strong nuclear force, we need to recognize that it's a very powerful force. It is the source of energy of the universe in the sun or stars, which are very large. It is also the source of energy for thermonuclear weapons. That little photo up there is from the Castle Bravo shot, the largest surface thermonuclear detonation by the United States at 15 megatons. It would also be the source of energy for fission power, but if we can go back for a second, note that on the far side where we have large nucleus going to smaller ones, it's not a big difference, but on the left side, if we have very small nucleus, like an H2 or an He3 going to the middle, it's a big jump. That's the source of power we're trying to find. Fusion is putting them together. So there, that's our little review of energy, some chemistry, and some physics. Today we're talking about the physics side, the strong nuclear force. So I've got a little graphic up here that shows both fission and fusion. And fission is breaking apart. That's what happens with nuclear power that we know of today. That's the nuclear power plant down by South Haven. Fission, we're taking uranium and splitting it apart. Fusion would be taking smaller atoms like deuterium, that's a proton and a neutron, or tritium, that's a proton and 2 neutrons, and pushing them together. This is the source of energy we want to see if we can tap to be the future for mankind. Now, for just a moment, we're going to have to pause on that part of the problem and talk about states of matter. And there are three states of matter that we're mostly familiar with, and then a fourth state, and the fourth state's important for us for nuclear fusion. So we have solid, liquid, and gases, and I think we all get a sense of what solid, liquid, and gases are. But the fourth state of matter, which tends to be by far the most form of matter in the universe, because it's the matter that's in stars, is a plasma. And a plasma is a form of matter where all those electrons are stripped off. I'm left with the ions, and they're floating in a sea of electrically charged particles. Plasmas exist at very high temperatures and high pressures. Plasmas do not naturally exist inside of our world as we know it. We can create plasmas, but they don't naturally exist in our world. But what's important is because the electrical charge has been stripped off, I now can interact with the plasma using the electromagnetic force, because I can pass a charge through the plasma. And that means specifically, and we'll see where this comes into play in a moment, that I can interact with my plasma from a magnetic field. I can talk to, as it were. I can control the plasma with a magnetic field. Typically, I need pretty powerful magnetic fields, but I can use a magnetic field to interact with a plasma. Okay, plenty of physics in this one. We won't go into any in detail. Suffice to say, what we see here is a graph that talks about the total cross-section. That's a physicist term for probability of happening, of a fusion reaction between a couple of different nucleons, or, nucleons is plural for nucleus. So it could be the D here stands for deuterium, that's a proton and a neutron. The T stands for tritium, that's a proton and two neutrons. Or the helium-3, 2 protons, 1 neutron. And what we find is that the probability of happening, coupled with the energy output, is much, much higher if I start with a deuterium and a tritium. Those are the things I really want to try to put together here on Earth to generate this nuclear fusion energy. I could do it with some other species, the D and the D together, but I get a lot less energy out for the same probability of event. That's important as we sometimes hear and explore what potential new people or new researchers are postulating for fusion. Useful to understand there's some physics that are very hard to overcome if I'm not using deuterium and tritium. Also important to remember, tritium has a 12-year half-life. It does not naturally exist on the planet, and I have to make it if I want to use it. And that comes into play as well. Okay. I need 3 things to exist together if I'm going to make fusion happen. It has to be very hot. It's a little bit hard in our world here today to really think about what it means to be 100 million degrees, but it has to be very hot. I have to get this stuff very close together, and I have to hold it there for some period of time. And very close together, remember that little story about the neutron? And if I strip all the space away and I have a teaspoonful of neutron star and it weighs as much as a battleship, well, those little pieces, those little atoms, protons and neutrons, they are very small. So I have to get them very close together because I have to have them interact. So we'll talk a little bit about how we get hot, and we'll talk a little bit about how we hold it together long enough. There are 2 ways in which we, the scientific community, have figured out how to hold our deuterium and tritium together long enough to make them undergo nuclear fusion. The first of which, figured out long ago, is called inertial confinement. Okay, so inertia is mass that is in a place and it tends to want to stay there until you have to act on it with another force. That's inertia. We want it to be right where it is and not go somewhere else. And in the little graphic behind me, we see this notion that we could imagine having some fusion fuel in a small space. In the case of the National Ignition Facility at Lawrence Livermore National Laboratory, the world's most powerful laser, that little fusion capsule is a 2 millimeter diameter BB. It's not really a BB, it's a super expensive carbon-coated sphere, but that's how small that little target is. And I'm going to hit that with the world's most powerful laser. I'm going to dump all this energy in there, and it'll then throw off the outer material, squeeze the stuff on the inside, and lo and behold, I can hold it together long enough because it's already there, and it doesn't have a chance to move to undergo nuclear fusion. And so nuclear fusion has happened at the National Ignition Facility, but as you might imagine, a 2 millimeter sphere of fuel acted upon by the world's most powerful laser isn't a particularly productive way to try and get energy out that I can then turn on the light switches. Some would say that we are not really sure what we know about inertial confinement fusion, and I'm here to tell you that it turns out we actually know inertial confinement fusion really well, and the United States of America can do all the inertial confinement fusion it needs to do for all eternity. It's exactly the technique we use in the thermonuclear portion of a weapon. But that's not particularly useful to the rest of us. We know how to do it well. It's a lot of energy. It comes out very quickly. It's very destructive. Well, what's our other technique to hold our fusion fuel together for a long enough period of time for it to act? And that's called magnetic confinement fusion. And there's a couple of different ways that we can create this magnet space to hold it together long enough for the fusion to interact. And this is a graphic of a tokamak. That's a Russian word for toroidal chamber acted upon by magnets. And if you put enough magnets around this donut shape, you can then, because we are passing that current through the plasma acted upon by a magnet, and we can squeeze the plasma and hold it in place. Now, there's a couple of things we need to have, besides just holding the plasma together, to have it undergo nuclear fusion. One of the keys of which is heating. We need to get hot enough, remember that 100 million degrees. And so just for a couple of simple graphics, I've shown a couple of the pieces of equipment at an experimental thermonuclear fusion reactor where we're going to generate some heat for our fusion fuel. And let's see if I can show. These are two different pieces of equipment. There's two different scales here. And right there is a picture of a man on this scale. This is called a neutral beam injector. And this device is actually a full linear accelerator, and then I add the electric charge back on as I do my linear accelerator. So this is like a $100 million or $200 million piece of equipment, and I need a couple of those for my experimental reactor, just to get heat into the plasma to try and get it hot enough. This device right here is a little bit smaller. This is called an ion cyclotron resonance heating unit, and this unit works a little bit like a very powerful FM transmitter. Turns out there's some resonance inside of our fusion fuel, and if I throw something like FM on your 54 FM on your dial, 54 megahertz waves at this plasma, I can heat the plasma. Just for comparison, for those of you who listen to FM radio, the most powerful FM radio stations are usually around 50,000 to 100,000 watts. At the experimental reactor where these ion cyclotron resonance heating units are being deployed, they're 20 million watts apiece. So I have to have a lot of power and a lot of heat in order to throw that into the chamber to reach those 100 million degrees. One last thing I'll mention about fusion before we get into some other challenges is that when I take that deuterium and that tritium together, mash them, I get helium. My helium is where the energy is. There's also a neutron. The neutron is not charged. I can't act upon that neutron with a magnetic field. It just flies out. And it turns out that high-energy neutron does a lot of damage to a lot of things. So some would say that there really isn't any radioactivity associated with nuclear fusion the way there is with fusion. And that would be mostly not actually true, because I'm going to make everything around my fusion reactor radioactive with all these high-energy neutrons, and it's going to beat the bejeebies out of all my material. Okay, fusion. Let's see if we can talk just a little bit about how I have to get electricity out of fusion and what some of the challenges are. So as a little reminder, how do we get electricity? Well, the vast majority of our electricity really is generated in the form of heat that then boils water, that gives us steam, that spins a turbine, that spins a generator. Like in the photo on the right, we have a 1,000-ton generator spinning at 1,200 RPM with multiple poles that has a lot of mechanical inertia moving in it. And that's what gives us alternating current electric power at 60 hertz in the United States, 50 hertz in much of the rest of the world. But the entire world uses alternating current electric power, and this is the way it's largely generated. If we look at the energy sources used to generate electricity, we see nuclear, natural gas, and coal. All of those are just used to make heat, really. Well, if I wanted to use a fusion reactor to generate electric power, I need to have heat. I've shown here a cross-section of the world's most expensive and largest scientific experiment, by far. This is a cross-section of the International Thermonuclear Experimental Reactor being built in southern France today. Construction was first started in 2014, and there are experiments at this device planned all the way up through 2045. The hope is it will become operational somewhere in the 2030s, after on the order of $14 billion is spent. It's a very expensive and large machine. And this machine, we can talk a little bit about some of the parts of it. Let's see if I can find the man. Let's see, right there is the man on this machine. And this space right here is the tokamak where the fusion fuel will go. There is no provision in this multi-billion-dollar machine to actually get heat out, to make steam, to make electricity. This is just to try and figure out fusion. So you might guess there's some challenges involved here yet. Okay, if we were to get power out of this fusion machine, how much power we need to get out so that we have all this excess heat so we can actually generate electricity? I've shown on the graph above two historical machines that have been used to generate fusion reactions and the promises or the plans for ITER, the International Thermonuclear Experimental Reactor. And what you see is the total electric power that has to go in and the estimated fusion power that comes out. And what you observe is that for the ITER machine, if I could get heat out of it, I might be able to get about as much heat out of it as all the electric power I put in. But remember, I still would need to convert that to electricity if I could do something with it. So these machines have been so far, and currently still are very large, very expensive, and consume a great deal of electricity. Because what? I have to generate all that heat with these multi-billion-dollar linear accelerators and ion cyclotron units and so on. I'll go back for just a moment and mention one other thing here in the ITER cross-section. This color represents the cryostat, cryo, cold, vessel, because I need the world's most powerful magnets to control my plasma. Those magnets are superconducting, so I need to hold those magnets at liquid helium temperatures in order to maintain superconductivity to have those powerful magnets. Remember, on the inside of this device, I'm going to try and have the sun, so to speak. Yes, you might imagine liquid helium on the outside and surface of the sun temperatures or center of the sun temperatures on the inside is a bit of a problem. Okay, there are a few technical challenges beyond which that I've already mentioned, we'll briefly touch on if I'm going to make electric power with a nuclear fusion reactor. The first of which is plasma stability. I've just got a simple graphic of a tokamak up behind me. It's kind of fake. It turns out that if I actually had a burning plasma inside of the tokamak, the burning plasma is radiating in the X-rays. We wouldn't see light coming out of it because we don't see X-rays, but in any case, useful to point out that plasmas all operate at the speed of the sun. If I'm going to have a burning plasma, it is speed of light, that it's all moving and interacting with speed of light function. And that means that my ability to control it is extremely challenging because it happens and moves so fast. Think sort of, again, the surface of the sun and solar flares. We're trying to take that and put it down into something that we control. Plasma instability, probably the single most technical difficulty challenge in fusion reaction. But I have a few others. Once the fusion reaction occurs, I'm going to have helium. I got to get the helium out. That's taken out through a concept of something called a diverter. This is the cross-section of what that tokamak chamber would look like in ITER. And down here, I need to draw out my helium. And that helium is very energetic. It damages material extremely well, and it's very hot. So I have to figure out how to take that helium out. I have other challenges, one of which I mentioned is tritium. I'm going to use tritium. I need to breed the tritium because I don't have tritium around for forever because it has a 12-year half-life, so I have to cycle some lithium into a blanket wall inside of the fusion device, throw neutrons at it, try and get tritium, and then I have an entire tritium plant used to create that tritium or pull the tritium out of the fuel. I also have all these neutrons. They're going to hit that first wall. They're going to punch holes in it, so to speak. On this cross-section they've shown somewhere in here, I might have coolant one day for this device to actually get heat out and make electricity. So there are several other challenges. And again, in this cross-section they'll show the vacuum vessel because I have to have a perfect, near perfect vacuum in here, because if I don't have a near perfect vacuum, I won't be able to hold the heat in because I'll have conductive heat transport to get the heat out of the plasma. And then the last little thing I'll mention is all of the thermal loads. We've just sort of briefly touched on that. I have liquid helium temperatures on the outside, surface of the sun temperatures on the inside. If in a perfect world I can make this device just go, then it all reaches some sort of nominal thermal stable state. And, you know, like a big boiler in a coal plant, once it's all in a stable state, it can just stay there, but that's not really how it works. I tend to have to need to pulse these in order to get the helium out at the diverter and other issues. So there's large thermal loads associated with the device. Okay. We've done about 30 minutes of nuclear fusion, and we'll briefly touch a little bit on the climate. A little chemistry and physics for our climate. Really our atmosphere, because if we understand the atmosphere, we understand most of what we need to know about our climate and the temperatures of the surface of the Earth. Very complicated diagram. I'm not going to go through all of it. But suffice to say that we live on a magic planet. It was created perfectly to have a set of temperatures on the surface that allows life to form. And it doesn't have to be that way. A lot of energy comes to our planet in the form of solar radiation at various different wavelengths. A lot of that energy is reflected right back to space. But if all the energy that came to the planet was reflected back to space, we'd be ice cold and we wouldn't be here. And I don't mean ice cold, I mean really cold. We need the atmosphere there to serve as a blanket to help bring the surface temperatures of the Earth up to a place where we can survive. And there's a lot of complicated physics involved in this perfect atmosphere. But this is the key one right here, this radiation back to the atmosphere that then comes back down because we've increased the wavelength of that radiation after it bounces off of the Earth, and after its wavelength is increased, it can then bounce back off of, say, a CO2 molecule, an H2O molecule, or a methane molecule, and then it warms our planet up. And so that part of it is kind of simple. And you've probably all heard about this. Well, the sun comes down, and the heat comes in, bounces off, back to the atmosphere, and back down, keeps us warm. Just for comparison's sake, we do need to talk a little bit about our magic perfect Earth and what our surface temperatures have been. And there's been some geologic understanding in the last 20 or 30 years of what the long-term history of the surface temperature of the Earth was. And it turns out, for most of the time of which life has been on the planet Earth, the Earth has been warmer. Quite a bit warmer, it turns out. More than 10 degrees C, which is a lot warmer. Now, I think we can be thankful for that because when the surface of the Earth is a lot warmer, vegetation tends to grow better in warmer conditions. And all that vegetation, over the course of periods of time in the past, became natural gas and oil and coal that we're using today. And so now we understand a little bit about this atmosphere and how it works with solar heat to keep the surface of the Earth at temperatures that we like. Let's talk specifically about greenhouse gases. There are several, and on this slide there's actually a point at which we should be able to pat ourselves in the back. Those of you who are old enough, which appears to be most everybody in the audience, by the way, can probably remember the 1960s and the ozone hole in the early 70s. And we discovered that we were producing a great number of chlorofluorocarbons, and those particular molecules would go up to the atmosphere, and then they would interact with ozone in the ozone layer, and a hole formed in the ozone layer. And there was a period of time in which we believed we would destroy humanity because we would destroy the entire ozone layer, and without that ozone layer, we're all going to get really sunburnt really bad because that ozone layer absorbs quite a bit of UV radiation. That was a success by humanity to stop the production of the chlorofluorocarbons, which is also good because those particular molecules are extremely good at reflecting heat back to the Earth. But there aren't very many of them anymore in the atmosphere. What there is, though, is a lot of carbon dioxide and a lot of methane. And those do help reflect heat back to our surface. So that's simple physics. If we have more of those kind of gases in the atmosphere, the surface of the Earth will get warmer. It kind of has to be that way. So what's just happened in the last period of time with the surface of the Earth? What we see is in the last 2,000 years, there's been a lot of variation in the global surface temperature. This is based upon archaeological evidence of certain little diatoms and other small life forms. And then, recently, the planet has gotten quite a bit warmer on this scale. And in fact, the last 9 years, as of 2022, were the warmest on record. This is the last 100 years. And we see that the Earth is getting hotter. It's just simple physics. And there isn't really a way to have that not happen, as long as we're going to have more CO2 and more methane, those two in particular, thrown into our atmosphere. Okay, we're nearing the end of the little story here. Global electricity production. We're going to try and put these things together a little bit. So let's talk about electricity and why is electricity important, how that fits into the picture. So energy, total energy. Not surprisingly, global energy consumption by humans was pretty much flat since we started farming all the way up until about the 1800s. And we figured out that there was something called coal out there, a fossil fuel. Until that time, humans had burned wood, and when you're just burning wood, there's only so much energy you can get. And then we figured out coal and natural gas, and there's other sources of energy on there since then, and so global energy consumption has gone up considerably. Now let's specifically talk about electricity, because electricity is a super useful source of energy. One of the things we can do with electricity we can't easily do with other forms of energy is we can turn motors. And if we can turn motors, we can compress refrigerants. And if we can compress a refrigerant, then we can have refrigerated air, AC. And it turns out humans really like that. Because without it, buildings in warm parts of the earth can get really hot and they're uncomfortable for us. And what we see on this graph is electricity consumption in various different countries over the course of time. Suffice to say, the US is the winner in electricity consumption. We consume electricity really well. That's maybe not that good, but it's what we do well. But of course, we live well. And it's maybe not a surprise that places in the world you might choose to live are places that consume a lot more electricity, and others maybe a little less so. Everywhere, electricity consumption is going up. So if I look at what I expect total energy demand to be in the future, most of that will be in the form of electricity because electricity is so valuable. Electricity is what gives us also computing and AI. And for those of you who have traveled internationally, you know that everywhere you go, people are on their cell phones and something has to drive that cell phone. Finally, where's human population going? It's going a little bit different than we might have thought 40 or 50 years ago, and that's probably a good thing. There was, a scare for some period of time that humans were going to completely overwhelm the planet, and that's a little less thought of today. But what we see is population growth is in between the tropics, near the equator, everywhere on the planet Earth. And so, more people are going to be living in the future in places that are hotter. I think I'll skip this slide. We'll talk about it if we want to when we're out there. That was something about renewables, and we'll just get to this. So what's the projection for electricity consumption for the next period of time? Of course it's going to grow, and it's going to grow in Asia and Africa and other places, mostly in Asia. Look, there's over 1 billion people in India. There's 500 or 600 million people who live in Southeast Asia, Indonesia, Vietnam. They mostly don't have refrigerated air. I was just in Vietnam a couple of weeks ago, June. Refrigerated air is really nice when you live in Vietnam, let me tell you. It's hot there. It's hot there all the time. Okay. We're just going to put it together then. It's my last slide. And I feel a little bit like I'm letting you down. But hopefully we've talked a little bit through the technology and some of the challenges and what's happening with our atmosphere and climate change. And so I'm just going to put the only slide up here that has bullets. I've tried to not have that for you. Controlled thermonuclear fusion. Pause for a moment. Controlled is important because it turns out thermonuclear fusion on Earth, we actually can do that well, but not in a way any of us ever want to see again in our lifetime. controlled thermonuclear fusion is very, very hard. It is like taking a chunk of the center of the sun and putting it inside a chamber and controlling it. If we thought we were going to have controlled thermonuclear fusion to generate a steady state heat source, because that's what I need to generate electricity, well, those hurdles for that challenge are even harder yet. There are all kinds of them. The International Thermonuclear Experimental Reactor, ITER, being built in France, is the world's most expensive, by far, scientific achievement experiment. And it won't even get there. Plus, we have to do this a lot if we want it to actually generate electricity for us. If, on the other side, we talk about climate change, look, it's just simple physics. It always has been. That's why scientists have known for a very long time, if we burn fossil fuels, we will eventually heat the surface of the earth. There are things you can do around the boundaries, but the scale of the problem is hard to imagine. We burn millions of tons of fossil fuels daily. For those of you who live by the train line, you know that there's typically 100 rail cars of coal heading north to the Campbell plant every day. Right? It's a big problem. And oh, by the way, global electricity production will rise. Why? It has to. Why? Because there's 1 billion Indians, and they would really love to have the opportunity to sit in an auditorium with air conditioning, and they probably can't today. And all that refrigerated air, if you're somebody who lives in one of those tropical locations and somebody says to you, you can either have some cooled refrigerated air in your home, or you can support climate change. What are you going to choose? And so, sadly, but honestly, is nuclear fusion energy going to deliver electricity to help us meet the demands of our global climate issues that we face today? No. I don't believe it. I don't believe it in my lifetime. I don't think it'll happen in my children's lifetime. I actually don't think it'll happen in my children's lifetime. I'm sorry about that. But that's the chemistry and the physics. Thank you. We have time for a little.
How much are we spending as a country on that, developing this fusion, which will not work?
That's a good question. I do not know the answer to that question. I will say this. Spending fits into a couple of different categories. There's fusion research programs going on at most major universities throughout the country, funded through the Department of Energy. It is probably 5 times more than what is currently spent on fission, which would and could be an effective heat source for electricity production. But we live in a world where the government seems to be moved by clean and shiny. Yes, sir.
What about the experiments that are being carried out on cold fusion?
Cold fusion?
Yeah.
I haven't heard that term in a very long time. But if we dial back the clock, there was a big explosion in the scientific literature in the late 80s, middle 80s, about cold fusion, the concept that under the right conditions in some sort of electrochemistry cell, we can make deuterium and tritium come together. Pons and Fleischmann were the original authors of that story that made the big kerfluffle 40 years ago. 30, yeah. There hasn't really been any satisfactory evidence that cold fusion exists, or if it does, maybe it could exist at like a 1 or 2 molecule or atom by nucleus happen, but certainly not at scale.
Hello, is the Born-Haber cycle in the 1910s that created so much CO2 might be contributing to the global warming also?
Okay, so is that an online question, or I think I missed a little bit of the portion of the question.
I think the development of the Born-Haber cycle might have contributed to carbon dioxide in the atmosphere.
Yes. Well, any industrial process, one that consumes energy and two that also produces CO2 is going to contribute to global warming in that sending those emissions up. One thing I didn't touch on that maybe fits into the picture here is that we usually in the news talk about CO2, fossil fuels, and the need to get rid of carbon combustion in order to address global warming. But as you, let's see if I still have this up. Nope, wrong direction. Let me throw this graph up here because it's kind of that one. Methane is a huge contributor because the methane molecule is even better at reflecting heat back down to the surface. And all of that methane, or the vast majority of that methane, actually is from animal husbandry and animal use or farm use or land use. More of it than from oil and gas production, it turns out. Cows belch a lot of methane. And so, if you were to choose lifestyle choices to reduce your global warming footprint, what's the number one thing you can do? Eat less beef. Weirdly, that's what makes the biggest difference for an average person.
I have two questions.
Okay.
One is rationalizing the global climate change over 300, 400 million years. Your next slide, which is 18 degrees. The one, 300, that one. Okay. So we didn't have cars, we didn't have air conditioning, and things changed 18 degrees.
They changed a lot. Yeah, this is two factors. A little bit is the power output of the sun, because these time scales here are so great that the solar dynamics actually matter. So that's a little bit of what's happening. Most of what the thought is for the driver of the large-scale increase in temperatures in the past, though, is geology. A little bit also, you know, the plate tectonics, what is the surface of the Earth has changed in time. You know, if we go back to the Paleozoic area, all of the land mass on the planet Earth was Pangea. It was all in one supercontinent. And so that changes remarkably what we think of as the surface temperature of the Earth when it's all one giant continent that sits on one side of the planet. But a lot of this is geology, so over the course of these kind of timescales, we can have periods with vast quantities of sulfur coming out of the Earth in volcanoes, and that will then throw lots of particulate matter up into the atmosphere and change the dynamics. But remember, we're talking about very, very large timescales here, right? And that's why these numbers can be pretty big in time.
The second question is a source for nuclear energy, specifically thorium in lieu of plutonium and uranium. Doesn't have an explosive element, nor does it have a radioactive element per se. So why isn't the DOD and the DOE going down that path?
Well, thorium will. So the way we get energy out of thorium is we're going to fission it. We're going to split our thorium. And thorium is kind of nice from an arms control perspective, as much as that's valuable, in that I cannot take thorium and convert it to an explosive fission reaction. I can't do the same thing with uranium as long as I can keep my enrichment in uranium below 93% either. So really, all of our uranium reactors in the United States all run at enrichments of a few percent, and that fuel, as long as I can control enrichment technology, also has no impact in an arms control perspective. So I would say the benefits relative to arms control and nuclear weapons with thorium versus uranium are very, very, very limited, although arguably they exist. But I still get the same fission reaction, I still get the same fission products, I'll still have spent nuclear fuel with a thorium reactor, like I would have with a uranium reactor.
On your global warming or gas emissions slide with the pie chart, if I understand that right, that is in terms of mass of emissions.
No, this chart attempts to describe the contribution to the greenhouse gas effect.
To the effect, okay.
Yeah, which is why total mass of methane is markedly less than CO2, but its impact is greater because it is a better reflector of heat.
Okay, well, methane emissions from the from the ground are a huge factor, such as in Siberia, there's a great big crack somewhere that spews out enough methane to possibly overwhelm what the cows produce. What do you say about that and what we can do about some of those kinds of things?
Well, I would say that anything we can do to control methane emissions will be helpful for the global warming impact of that gas in our atmosphere. And methane can come from multiple sources, one of which is oil and gas production. And so it certainly is advisable that we implement regulations to control methane from gas production. Remember, when we see that methane being flared off, once it combusts, it's no longer methane. We want to control it before it's combusted. Most methane thrown into the atmosphere is from animal husbandry and land use. Deforestation can have an impact. There are some thoughts of other large-scale potential methane sources. One thinking is that there's a lot of methane entrapped in permafrost, and if we get to a certain point in temperature in places where there's a lot of permafrost, there could be excess methane emissions. So I think in many ways, if we, as a society, want to have some more near-term changes to reduce the impact of global warming, methane is probably a better place for us to be spending time and energy and money.
Stephen, thank you very much. It began.
Thank you.
It was over 2 years ago, to be exact, that one of the members of HASP posed the question of, I'd like to learn more, and maybe our members would, about nuclear fusion. Who do you know? And somebody gave me Stephen's name. Well, I didn't know him, but I knew George was a member, so I called George, and George gave me Stephen's phone number. He was in Los Alamos at the time. He now lives in Holland, and we began this just so we can learn. So I hope today that you did learn a little bit more about nuclear fusion, and we learned that it may not be the solution unless we are all going to live a very, very long time to this climate situation. I want to remind you that next month, on September 3rd, we will have Johnny Rodriguez, Executive Director of Latin America's United for Progress, speaking to us regarding the Hispanic community and their part in the history and part of Holland. And then September is a busy month because we have 2 monthly programs in September and none in October. So 2 things, check your HASP happenings. And then last, remember today, August 6th, is primary day for voting. And we all want to be good citizens and vote. So if you haven't already done it, please head to the polls and vote. Thank you.